All right, so we started off the year talking about atoms, specifically their nuclei and the electrons, and then we talked about how those electrons can bond with other elements, and then we talked about how those compounds that are created interact with one another with respect to intermolecular forces, and then we said how those intermolecular forces, if really weak, can form gases that behave according to the ideal gas law equation. And then we said, wait a sec, if we have these atoms, we can react them together in certain ways to cause reactions to happen. And those reactions happen in such a way where they follow the law of conservation of mass. So for example, if we take a typical reaction, like the combustion of hydrogen to make water, okay, we see here that in order for this reaction to be true, okay, you need two hydrogens to react with one oxygen to make two waters. Now you can scale this down, but this is the smallest whole number ratios. These are moles, okay? So we can have various numbers of moles. If we had one of these, we'd have 0.5 of these, and we'd have one of these. If we had 4 of these, we'd have 2 of these, and we'd have 4 of these. But the mole language is not used with people outside of chemistry. They're going to use language of mass in grams or language of volume liters. So what we need to do is a process to use a chemical reaction as a recipe. Okay? Treating this as our recipe, not what we have, but just the lowest whole number relationship of the reaction. Okay? I have a recipe to make cookies. It doesn't mean that I always have those ingredients in my kitchen. Okay? So that's the recipe. We're going to use it, keeping in mind that the world likes those units. Okay? So let's do an example of a problem like this. Let's say, let me use blue here. We have the reaction between two common things. Okay? It's called the Haber process. It's how you make ammonia. Okay? Now we know the very first step of this process is to balance this reaction. Okay? So I see here that I need 2 here. That means I need 3 here, and that's going to be 1 there. So for every 1 mole of N2, it requires 3 moles of H2 to make 2 moles of ammonia, or NH3. Okay. So now I'm going to do my ice table, and this is a table that's going to allow me to keep track of not only how much I make, but how much is left over. Okay. So we say what we initially have here. The reaction changes, and I move to the end of the reaction. Everything on this side is going to go down, and every side on this side is going to go up. So what goes in this box here, these always have to be mole values. Okay? And what comes out of this box is going to be whatever the problem asks you for. Okay? So let's say the problem says you have 14 grams of N2. Well, we know that there's 28 grams in every 1 mole. So I have 0.5 moles here. And let's say you also have 14 grams of H2. Okay? We know there's 2 grams for every 1 mole. So that means if I have 14 grams here, that means I have 7 moles. Okay? 2 grams for every 1 mole is equal to 14 grams for every X mole. 14 divided by 2 is 7. And I have 0 moles here. So now, in order to complete this problem, I need to figure out who am I going to run out of. Because the one I run out of is the one that I'm going to use to find X, and thus find everything else. Okay, because much like the peanut butter and jelly discussed in class, it determined how many sandwiches I could make, not the bread. So I look at this, and I can first do it the conceptual way. Okay? The recipe, this is not what I have, but the recipe calls for 1 N2 for every 3 H2. Okay? So here I have 0.5 moles of N2, and I have 7 moles of H2. So on first glance, it looks like it matches up. You always need more H2. I got more H2. But I got way too much more H2. Way too much more. So I only need 3 times as much H2. So really, all I need here is 1.5 moles of H2. But I got 7. Way too much. We can use the Emily method. So 7 times 1 here is going to be 7. And 0.5 times 3 here is going to be 1.5. That's the larger number, so that's the one that's going to get the 0. Okay? So now that I have that, I can set up my ice table. This is going to go down by x, this is going to go down by 3x, and this is going to go up by 2x. Okay? So I can now solve for x here. 0.5 minus x equals 0. So x equals 0.5. Okay? I can plug that 0.5 back in there. And this is now going to be 1.5 moles here. And this is going to be 1 mole. So now, if 0.5 moles of N2 and 7 moles of H2 combine, I'm going to make 1 mole of ammonia, NH3, and I'm going to have left over 1.5 moles of H2. But the problem is going to ask me now, how many grams of NH3 is produced? Well, I know that this is 14, so we have 17 grams here for every 1 mole. And here I have x grams for every 1 mole. Ooh, perfect. I have 1 mole. So this is going to be 17 grams of this, and the rest of the world will understand that. Now here I have an option. I could either convert this to grams, or I can convert it to liters. If I converted it to liters, I would plug it into PV equals nRT. If I converted it to grams, I would simply just set up a relationship like this. Now, this one would make sense to use PV equals nRT, because if you look at the Lewis structure to this, it's ideal. It's very small, it's nonpolar, it only has London dispersion intermolecular forces. If you look at this one here, it's a pyramidal molecule, and therefore it's going to have these partial positives that are there, dipole-dipole forces. Okay. This also can work in simple reactions where we just have decomposition. So let's say I have a simple reaction where we have H2O, and H2O now is just breaking up into O2. Okay, so we're looking at it through, let's erase that, let's do it in blue. So now we have the reverse situation where this is going on, and we still need to balance it, okay? ICE. Okay, so now let's say we did our gram conversion here, and we end up with, let's say, 0.25 moles, 0, 0. So now the question is, if you decompose water via electrolysis, how much H2 and how much O2 will you make? So in a situation like this, you only got one thing, so it's really easy. You're going to run out of it all. And this is going to be plus 2x, and this is going to be plus x. So the only time you have to think about who is excess, who is limiting the reaction, Emily's rule, the only time you have to think about that is when you have 2 or more reactants. Okay, so this is now going to allow me to solve for x. 0.25 minus 2x equals 0. So 0.25 divided by 2. And when I do that, so it's 0.25 divided by 2 is 0.125. So 0.215 times 2. This is going to be 0.25 moles. And this is going to be 0.125 moles. Okay. Both of these now I could use PV equals nRT, or I can convert it to grams, however.